All right, hello and welcome. Today is Monday, May 11th. It's day one of AP exams, but you guys are not up until Thursday. My APC students are taking their tests today. So we AP1 have a little bit more time to prep, so we're going to use as much time as we have. We'll finish off our MyAP FRQ review session today with Unit 7 and then talk about one of our quiz questions, the mass on an elevator. Is there a stream tomorrow? Yes. So, and then Wednesday and Thursday, no streams. And then Friday, we'll catch up. Um, well, I mean, usually we're done before 11, and you can always watch the VOD if you don't catch the live stream. All right, so let us not waste any time. Today we will, well, tomorrow won't be as heavy as today anyway. So today we will first go over Unit 7, talk about the quiz. Tomorrow we'll talk about the rest of the quiz stuff, and then do a walkthrough of the platform. So if you're already taking the test, you probably know all about the platform. But for those who haven't taken a test, then tomorrow would be more beneficial as we'll go through the platform. If you want, you can actually watch the AP Physics C video from last Friday, and I pretty much walk through the College Board platform on for the AP test, how you're going to answer questions and stuff, etc. So you can probably watch that if you want. But again, we'll go through the walkthrough tomorrow to make sure everyone knows what to do and give you minor suggestions so that we can maximize our efforts. All right. So Unit 7 is today. So let's get started. MyAP Unit 7. And then from there, we talk about our final. The final is on the 22nd. Remember, there's no traditional final on finals day anymore because laptops and everything will be collected after Memorial, or is it Memorial Day or Labor Day? I keep getting those mixed up. Chat, is it Memorial Day or Labor Day? I guess it's Memorial Day. Yes, it's Memorial Day. So after Memorial Day, laptops and stuff will be collected. So nothing new will be given after the 22nd. The last 2 weeks are just Q&A weeks. So if you have any issues, we can go over. I'm going to be grading and putting up your final grades and stuff. All right. Let us begin with Unit 7. Unit 7 is Rotational Dynamics, and I have a strong feeling that... Uh-oh. Hang on one second. All right, back. Rotational dynamics is probably going to be on the AP test just because it combines so many things with dynamics and well, I guess with FP, like you can basically do everything with Unit 3 and energy along with rotational dynamics. So here we go. This question is a long free response. In their physics classroom, students want to hang a heavy sign of mass ms and length ls as a function, as shown in the figure above. The sign makes an angle theta with the wall without any support. The sign would rotate clockwise while its pivot rotate. The sign would rotate clockwise while its pivot would remain connected to the wall. Students can connect one support cable vertically from one of the hooks above the sign as indicated by the dotted lines in the diagram. So we've done a shelf problem, the MIT question shelf problem before. So this is similar. It's actually easier in that the cables are straight and not at an angle. So question, and then all right. So question A, or part A, rank the 3 hook locations according to the amount of tension the support cable would experience if the students decided to support the sign. Blah blah blah. Okay. Put 1 as least, 3 as most. Okay. If 2 locations would have the same, give them the same ranking. All right. Let's talk about the shelf question. And similar to the MIT quiz question we've had, if the shelf, so here's our pivot along the wall, if the shelf is held by a cable at an angle, okay, then the pivot force will have 2 components, like an X component and a Y component, giving you an angled force at the pivot. So Ft, then the pivot would actually give you some sort of angled force, F pivot P. And the mass, of course, mass would be straight down from the center of mass. But here we have it pretty easy in that the shelf is nice and flat, and all the tension cables that can be put on the shelf are all straight and vertical. One thing to note is angle is actually over here, and that will be important later on. So here's our general, oops, there it is, design, and all we have to do is figure out what our tension is. How do we do that? Well, with the rotational dynamics or static equilibrium problems, remember you can choose the axis of rotation, so choose wisely. Of course, we're going to choose the pivot force as the axis of rotation, or not pivot force, the pivot itself as the axis of rotation. Like so. And that way, only the forces that are not on the pivot will apply torques. Here's mg. Mg, of course, is at the center, and we can have various locations for the other 3. Doing sigma tau. Sigma tau will show us that there's a clockwise and a counterclockwise torque. Okay, so all the things that are pulling down, or all the things, mg that is pulling downwards will provide a clockwise torque, whereas the tensions, all the tensions will do a counterclockwise torque. Okay, so torque, of course, is force and or the radial arm, or the r vector. Now, the angle between r and force are all 90 degrees, right? So we don't have to worry about the cross product. Sine of 90 degrees is just 1, so we're going to get maximum torque from all the forces. All right, so we'll do counterclockwise minus clockwise. So the tension force, whatever the tension force is, times the distance, r, times sine of theta, but sine of theta again is 1, minus mg, which is the weight force, and mg is only halfway, so L over 2, and it's equal to 0, and therefore the tension force is going to equal 1 over r times, I'm going to write it this way so you can see, 1 over r times mgl over 2. Oh, I can't see the 2. Okay, so it's a 1 over r relationship, meaning the one that is further away, well, we'll have less tension in it. So Ft is proportional to 1 over r. So since the radius for C is greater than the radius for B is greater, oh what? Radius for B is greater than radius for A, then force must be the other way. So FTA is greater than FTB greater than FTC. Okay. Briefly explain your reasoning. The reasoning would be that the force is directly proportional or inversely proportional to the radius. Or, sorry, I shouldn't call it radius. You should call it the lever arm. Lever arm. Also known as leverage. So R is actually the lever arm. Okay. And so since C is further out from the pivot, then the tension in C is the weakest, etc. All right, now the students hang the sign, but it snaps, oh no, and it starts to accelerate and rotate clockwise. The diagram shows at 3 different locations. Let's see, at T1, T2, T3. Okay, so it's rotating clockwise now. Indicate at which time, if any, the angular acceleration alpha of the sign is greatest, or whether it is the same, blah, blah, blah. Okay, so as it's rotating, where is the greatest alpha? Of course, alpha is going to be equal to the net torque on the system divided by the moment of inertia of the system. Remember, torque is I alpha. If I take a look at the shelf, here's a pivot. Okay, mg is always straight down from the center of mass. Okay, but as the shelf rotates, the angle between the radius vector, or the lever arm, and the force increases. So here's r, and the angle between the 2 vectors is increasing. Okay. I'm going to call this something else, like phi, angle phi, because angle theta is already used up. So of course, when it was 90 degrees, when phi and this angle was 90 degrees, we had maximum torque, and therefore we would have maximum acceleration. So when we start off, so when it was horizontal, we had maximum acceleration, because as you can see, if we had r times force times sine of theta, and as sine of theta goes from 90 to 180, the value of sine of theta goes from 1 to 0. Oops, I should do this. As theta goes from 90 to 180, sine of theta goes from 1 to 0. So the value of sine of theta obviously is decreasing, and you get less and less torque, therefore you're going to get less and less acceleration. Okay. Meaning when the shelf is basically flat, when this straight downwards, then mg again is still straight downwards. This mg vector no longer provides torque on the shelf. All right, next up. So it's greatest when it's flatter, or when it's more horizontal. So at the start it was greatest, and the angular acceleration decreases as it goes downwards, turning vertical. So now you have to provide a physical explanation. So physical explanation would be kind of what we did. But you would have to explain it with words. So you would have to say things like the gravitational force has less and less leverage on the shelf as the shelf becomes vertically oriented, providing less torque on the system, which means there's less angular acceleration on the system. Something like that. All right, show that alpha can be modeled with blah, 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 the rotational inertia. They actually give it to you. Remember, this is a rod, basically a spinning rod. Rod from the side is 1/3 ml squared. Rod from the center is 1/12 ml squared. But this one's rod from the side. Show that alpha, basically solve for alpha is what they're saying. So let's go and solve for alpha. How do we solve for alpha? Well, start with your sigma tau equation. Didn't we already do that up here? Okay, whatever. So sigma tau, what torque do we have? We just have mg, no more tension because the rope already snapped. So mass times gravity is the force times distance, or the lever arm. The lever arm is halfway, so it's L over 2, LS over 2. And at any point, the torque is force times distance times the sine of the angle between them. Oops. Oh, I used theta here. I should have used phi. You could use theta. With theta is actually going from 90 degrees to 0, which does the same thing. So that was phi. Let me backtrack a little. Theta is going from 90 degrees to 0 degrees, and sine of theta goes from 1 to 0. So same thing is happening, whether you look at phi or theta. All right, let's see. Mg times distance times sine of theta, that's my torque. And it's equal to I times alpha. I is 1/3 ms ls squared, and phi moment. Yes, it's a phi moment. Alpha, and just isolate and solve. Just plug in. M's cancel, and then one of the L's cancels, and so you can see how alpha is. Oops, that's an A. Alpha is equal to. So I have 1/2 divided by 1/3 is 3/2, and then we have G sine theta over L. Okay, LS. So that looks this. There you go. All done. The students want to describe the angular velocity omega of the sine as it rotates, and they propose the following equation. So omega equals blah 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 times t. Regardless of whether or not this equation is correct, does this equation make physical sense? Ooh, this is an interesting question. This has been asked many times in the past, in past AP tests, right? What does physical sense mean? So you're not trying to prove whether it's right or wrong. You're trying to prove if it makes physical sense. So when the College Board gives you this term, physical sense, does it make physical sense? Basically, to you as a student, this means check the units. Okay, make sure the units work. All right, so the equation is omega as a function of time is equal to 3/2 G sine theta over Ls, which is alpha, times t. Right, so on the side, let me write it. Does omega equal alpha t? Well, this is kind of like our WOWAT chat. Do you guys remember the name of this equation? Which equation does this refer to? Now, they did take some liberties in that omega naught is 0. As the shelf falls down, it's going to start from rest. What equation is this? No one? Ah, tisk tisk. It is Mitch. All right, so let's check if it makes physical sense. to make physical sense, we have to make sure all the stuff cancels out. Now, omega is typically measured in radians per second. So we need to make sure that the other side is radians per second. The fraction doesn't have any units, so can ignore that. Gravity is meters per second squared. I shouldn't say gravity, I should say acceleration due to gravity near the surface of the Earth. Meters per second squared, and then sine of theta. Now we can actually modify sine of theta. And then which is basically going to give you a percentage. And then ls, it has meters in it times time. What does that mean? Well, what happens? Well, m's cancel. Time over s squared. Oh, I put time. I should have put seconds. Whoops. Time is in seconds. So this is seconds. This is meter. The m's cancel. One of the s's cancel. I have something over s, which is basically radians per second. Now, radians isn't really a unit. It's a percentage. It's a percentage. And so we're getting that percentage from the sine. Sine of the angle doesn't have a unit. Sine of the angle is your percentage. Interesting. So based on the unit cancellation, giving us hertz, basically 1 over s. Hertz is the units for our angular rotation, angular speed, or angular frequency, as we say in Shin. All right, students attach a rotary motion sensor. Hey, we have those. Record omega and theta and create a graph of the magnitude of omega versus theta. Oh my gosh. So this is not, now normally the rotary motion sensor will give you omega as a function of time and then theta as a function of time. So you can combine those two data sets and then graph omega as a function of theta now. But be careful, notice how they have theta in degrees and not radians. So keep that in mind. Make sure you always look at the units when you have a graph for each axis. Okay, so it says 4 students independently derive equations and propose them to describe the motion of the sign. Which equation best matches the data collected? Whoa, what is all this stuff? Okay, so omega is a function. So what's going on? Remember, theta is between the shelf and the wall here, so that's theta. We start from 90 degrees, and then as it rotates clockwise, theta decreases towards 0 degrees. So for the graph, we actually have to read from right to left. We start off from this 90 degrees here. So at 90 degrees, we have 0 radians per second, 0 speed, and as we shrink, we get higher and higher angular speed. And so at 0 degrees, we are going the fastest. Right? If you look at it from an energy perspective, our gravitational potential energy, pegma-ga, turned into kinetic energy. And we can talk about, actually, let's talk about it because it's not actually on this question. So for things that are falling, like this shelf, this is technically a APC type question, but might as well learn it. So if a shelf is falling and it's rotating downwards, like this, okay, what you want to do is look at the change for the center of mass. So the center of mass started at this elevation, and once it's nice and vertical, it's now at this elevation. So it started from here and it went down this much. How far down did it go? When the shelf falls down and turns vertical, chat, how far down did the center of mass fall? Hint. The center of mass is half the distance away. Yeah, it's L over 2. It's kind of like a radius, right? So when it's vertical like this, it's still L over 2. L over 2. So you can say that based on Pegmaga, your height is L over 2, and that's the amount of rotational kinetic energy you're going to get. So this mgl over 2 turned into Kakarot. Oh, sorry, not Kakarot, but just Carrot. All right, so there you go. You just did an AP Physics C question. Good job. All right, back to this thing. So again, we're going to look at it backwards from 90 towards 0. Notice how the acceleration uh, is decreasing, right? So at the start, we have very high acceleration. So our velocity, remember, we're looking at it going left. Our angular velocity increases very rapidly, but as it goes, as it gets flatter and flatter, as it becomes more and more vertically oriented, the acceleration decreases. And then once you hit 0 degrees for theta, which means it's perfectly vertical, you're not accelerating anymore. You've reached your maximum omega. All right, so what graph? Basically, they're asking you which one makes sense. Now you're going to get a calculator, right? So you could just take out all of the constants and then just look at the variable that can actually change. Remember, this is omega as a function of theta. So L is a constant, G is a constant, and these numbers and stuff are all constants. So let's take a look at these equations. So for the first one, 3G over L. So the first one is square. So omega is a function of theta. Square root of 3G over L, which is a constant, times square root cosine. So the first one is a square root cosine. No, you can't take the slope. I mean, acceleration is a time function. Um, you can infer the acceleration. You can't get the acceleration. Acceleration is over t squared, so you need a. If you take the derivative, your x-axis has to be time, not angle. But you can find the rate of change of omega as a function of theta, and so the rate of change of omega is decreasing, which can be related to the acceleration of theta of omega. Number two is 3ls. So again, there's this constant 3ls over g times cosine of theta. And then number 3 is 3g over L. 3g over L times sine of theta. And then the fourth one is square root 3L over G times square root of sine of theta. Okay, so we factor things out to simplify, so this should help, right? If you have a lot of stuff in your equation, try to simplify. With radicals, you can split the house. Split up all the constants and then take a look at the constants later. First, figure out what equation. So is it cosine or is it sine? Emma says, don't you know it is one of the cosine equations because the graph has a value of 0 at 90 degrees. So we know that at 90 degrees, cosine is 0. So when theta is 90 degrees, cosine gives you 0, which will give you 0 omega. Okay. So we're down to 2, because sine of 90 degrees will give you maximum. So we can cancel out the sines. So we're down to these two. 3g, is it 3g over L or is it 3L over G? Justify your answer by citing specific features of the graph. Ooh. So let's see. L, do we have anything about L? In physics classroom, the students want to hang a heavy, a heavy sign of mass ms and length ls. The sign makes an angle theta with the wall. Okay, well. Okay, so what does the, I mean, for this graph, what does the number in front, the coefficient, do to the graph? Right. Is it going to stretch it, or is it going to shrink it into the square root? Typically, for the most part, the difference is 3g over L versus 3L over G. Unless L is really, really huge, more than 9.8 meters or something like that. So you have a, I guess we would call this the big value, because 3g is big, and this is the small value. So because when you take the square root of a smaller number, it's going to be even smaller. But we also have to make sure it makes physical sense, right? Because just looking at values is not going to help us, because we can't map out unless you actually have values and you can map out the function with the numbers given. So let's just make sure it makes physical sense. G, so G is meters per second squared. So meters per second squared divided by meters gives me, it's all under square root, by the way. So the meters will cancel, giving me 1 over s squared, and then square root that, which gives me 1 over s. Yay, that works. So there you go. Because I want 1 over s for omega. Whereas the other one has meters over meters per second squared, right? Meters over second squared times. Oh, 1 over meters. There you go. In case you didn't know, remember you multiply by the reciprocal. All right, is that it? I guess that's it. So features would be, what features did we use? We used the x-intercept, so the 0. The function hits 0 at 90 degrees, and the function hits maximum at 0 degrees. So based on that, we were able to deduce it was a cosine function. And then for the constants in the front, we just made sure the units kind of worked out with 1 over s. Okay. All right, so that was that. Let's look at number 2. This question is a short one. Oh, yay, it's our favorite. Oh, no, I got logged out. BRB. Okay, Unit 7, FRQ, number 2. Well, that took way too long. Let's go a little bit faster so we have time to do at least one of the quizzes. This question is short. Okay, good. The ramp of height h0 is placed on top of a table that has an edge that is a distance h0, capital H0, above the ground. A student places a hoop of rotational inertia I hoop, mass m0, and the radius r0 at the top of the ramp as shown. The hoop is released from rest bubble. Okay, so it's basically marble down a ramp. Or in this case, it's not a marble, it's a hoop down a ramp. A classic. Here we go. The figure below represents the hoop as it travels along the ramp. Draw the force diagram that shows and labels the forces, not components. Okay, basically do an FPD. Rolling FPDs are really important, especially in AP Physics C. So we'll do more. And you want to draw them, especially for when you have rotational stuff involved. You want to draw it so that you draw the forces where they are applied on the body. Where they are applied on the body. There we go. So we're rolling down. We have some sort of friction, static friction. We're rolling without, rolling without slipping, I presume. We don't do with slipping in AP1. So recall that friction will always be parallel to the surface itself. The normal force is always perpendicular to the surface. So Fn is perpendicular to surface, and then FF is what? Why Microsoft is parallel to surface. All right, so the normal force, of course, is applied from where we have contact, and it's 90 degrees, like so. And the gravitational force is actually from the center of mass, which is interesting. Mg. And I want to make sure I draw the mg vector slightly bigger than the normal force, at least. Okay. And our mg is from emptiness of space, or pulling the object down. Oh well. Yeah. Chat, is it faster to roll down a ramp, or is it faster to slide without friction down a ramp? After it is released from rest, the hoop rolls down, launches horizontal. Oh, it's a horizontal projectile, not even. Oh, that's actually marble in a cup, right? Off the edge of the table and lands horizontally. Distance d from the edge. The situation is repeated, but the hoop is replaced with a solid disk of rotational I disk, mass m, blah blah blah. In a clear, coherent paragraph length response, blah blah blah. Predict which object, the hoop or the disk. Oh my gosh, is this a classic? Can we get a classic physics question hype train in chat? Sliding is faster. Good job, bubble guy. A classic physics question. So now, so what do we have? We have 2D projectile. This is D. It's marble in a cup. It's marble in a cup. All right. So when you do this, recall that we do peg-mega here at the top. So we start with peg-mega, but the peg-mega is based on the height differential. And the height differential is little h0. It doesn't have anything to do with how tall the table is. It's how tall the ramp is, right? Peg-mega based on height of the ramp. And then down here, our Vx is going to be based on how peg-mega turned into Kakarot. Kakaroto. I actually have a cool meme I'm going to show you after our AP test. Actually, you can just watch it tomorrow during the APC post-game analysis. Okay, and then from there we have this second part. In part 2, it is just a 2D projectile, 2D kinematics. Ooh, I like this pen. Actually, I don't. Never mind. All right, peg-mega was m. Oops, let's go back. Oh my god. mg h naught. So that's my energy. mgh naught turned into kekarot. Kekarot is 1/2 mvx squared plus the rotational energy 1/2 I. Make sure you use parentheses. It's really easy to mess up. Oh, you're not seeing anything. There we go. So we said it's pegmaga to kekarot. The velocity here at the bottom of the ramp is nice and horizontal because it's a horizontal projectile motion problem. So it's mgh0 is equal to 1/2 mvx squared plus 1/2 I omega squared. Now I is going to be different, right? We'll call it I hoop versus I disk times omega squared, and omega squared is velocity squared over radius squared. And just know that I is going to have I hoop. You know that I hoop is mr squared, and I disk, which is less because the mass is spread out. And you're gonna have to talk about all these, just like you did on your on your test question. 1/2 mr squared. So obviously the disk has less inertia. You don't have to worry about the radius. The radius is going to be the same. Now it has, so we have to be very careful here. We're saying that it has less moment of inertia because we're assuming that the mass is actually the same, right? It's just the hoop has all of the mass spread out at the edges, whereas the disk has everything spread out throughout the body. Now, if you actually made a hoop, what you would do is you would carve out mass from the disk to create the hoop in the first place, right? So when you're carving out mass, you're actually reducing the mass. Therefore, you are reducing inertia. A disk has less inertia if and only if the radius is the same and the overall mass is the same. Right? Essentially, the density of the material would be different here. So keep that in mind. Keep that in mind as you move on to AP Physics C. All right, so of course, the one with less inertia will be going faster at the end of the ramp. And with a higher Vx, it's going to go a farther distance. How do we figure out what D is? Well, we use kinematics. Voy vyajit. Voy is 0, Vy is unknown, acceleration is negative g. The displacement in the y-axis is negative capital H0. That's the height of the table. Time is time, and that's what we're going to use to figure out what our x equation is, Vx dxt. Remember, time is the same in both axes. The displacement traveled in the x-axis is d, what we're looking for, and Vx is based on your energy equation. Now, what is different? Should we actually do this? I guess we can. Let's start with the velocity x for, well, what is time? 1, 2, 3. 2d over a is time. Time is equal to square root 2 ho over g, and that's the same for both. And d is equal to vxt, so it's directly proportional to vx. So we just have to figure out what vx is. Let's do hoop. So for hoop, we have mg little h0 is equal to 1/2 mvx squared plus 1/2 times mr squared times v squared over r squared. All right, the r's cancel, the m's cancel. We have 1/2 vx squared plus 1/2 vx squared. And that's 1, and so root gh. Okay, now let's do disk. Vx disk. The only thing that is different is the moment of inertia. So mgh0 is equal to 1/2 mvx squared plus 1/2 times 1/2 mr squared times vx squared over r squared. The r squared still cancels, the m's cancel. What we have is 1/2 and 1/4. 1/2 plus 1/4 is 3/2. 1/2 plus 1/4 is 3/2. Nope. What? 3/2 on the other side. 1/2 plus 1/4 is 3/4. That's what I meant. 3/4. 3/4 of vx squared. I can't do basic math anymore. And then when you flip it over to the other side, vx is equal to square root of 4/3. Okay, so this is over 1, whereas this was 1, so we're faster. Yay, faster. All right, so that was it. Classic. Okay, we have just a little bit of time left, so let's do at least one of the quiz questions and start working on grades and stuff soon. Let's do the spring mass system, the first one. Spring mass system, you had like something to, well, it's basically just like our lab activity. So here's our spring, here's known masses. You can do it two ways. One way is to do a bunch of masses. Oops. Do a bunch of masses and then graph the displacement, which is in meters, and force, which is the gravitational force in newtons. So known mass times gravity. And then plot your data, find the slope. The slope is k. The other way is to use simple harmonic motion. Recall that T for spring mass system is 2 pi square root L over G. And so, oh, what? That's a pendulum. Chat, what's the equation for spring mass system? Okay. So that's our spring mass system. And then so find the period and then solve for k. So we've done that. You don't want to find the period just for one oscillation. Try to do a couple. So let it go and shim. Stretch it some x amount. Let it go. Remember, one revolution is when it goes through the middle, through the equilibrium point, goes back up an equal x amount, and then comes back down to the original spot. That's one revolution. 4 amplitudes worth of distance. Okay, so let it go up and down like several times, and then divide the total time by the amount of, so t total divided by amount of cycles equals, or revolutions, whatever you want to call it, equals period t. Okay, so you can find k that way. Now the hard part. A lot of you got part A. B and C was the hard part, apparently. We are now going into an elevator. We're going to take this pendulum system into the elevator. So let's say we just keep it on the floor, like so. And then we have our spring. Let's put our mass on it. So we know what k is now, but we're going to take it on the elevator. The goal is not to find the acceleration of the spring mass system or the velocity. You know, you can take a look at your shim notes. Recall that the maximum acceleration happens at max distance away. Maximum velocity happens at equilibrium. It's not about the spring mass system here. Part B and C is to find Vmax and A of the elevator using your spring mass system. So now it gets a little trickier, right? Okay, so when the elevator door closes and it starts to accelerate upwards, right? So we're going to go up. We know the acceleration is upwards. Okay, think about what's going to happen to our spring mass system. So when it didn't move at all, we've reached some sort of equilibrium point where, you know, kx up is equal to mg down and everything is stable. Okay, as soon as the elevator accelerates upwards, okay, that's going to cause a force onto the base of your pendulum system, which is going to pull upwards, or here, which is going to pull upwards, etc. And so the top of the spring of the stand is going to pull the spring upwards, which means that it will look like relative to the stand, it will look like the mass is actually stretched out even more. We'll call this x prime. So when the elevator accelerates upwards, the spring will overstretch to this new spot. So what we need to do is measure x prime. Okay, measure x prime. And based on x prime, we can figure out what the acceleration is. Acceleration, well, if we just do an FBD, the kx should be equal to mg. So if I write my sigma equation, kx minus mg equals ma, and so kx minus mg over m equals a. Okay, but not only that, in order to find v, we also have to use a stopwatch to measure time. Okay, so what time are we measuring? Well, we're going to start our clock when the elevator first starts to move. So the start is when we start, is t0, when the elevator moves. Okay, now when do we end? Remember, we want to end when we've reached our maximum velocity. When does that happen? When does max velocity happen? Well, maximum velocity happens when your acceleration is 0. Right? If your acceleration is not 0, then it's going to continue to change your velocity and so on. You're going to keep getting faster and faster and faster. So at some point, the elevator will stop accelerating. Not quite, bubble guy, not quite. At some point, the elevator will stop accelerating, and when that happens, the velocity will have reached its maximum. Okay, so stop at t final, which is when a is 0. Now the real question is, how do we figure out when a is actually 0 when we're inside the elevator? Remember, you can't look outside. There's nothing else you can measure anything relative to. So the only thing you can do is look at the spring mass system. Okay. All right. So the elevator is going to accelerate. Usually it's going to be a gentle, small acceleration. You just, it picks up speed and then the acceleration is gone. In reality, the acceleration has a decaying function, but that's not an AP1 at least. Okay. So when it is accelerating, we see that the mass is going to stretch out the spring, and it'll be very quickly. It'll happen really quickly, I mean. And then it'll reach this x prime distance, and it's going to stay there. While it's accelerating, it's going to stay at x prime. As soon as you stop accelerating, right, there's no more tug on the spring, and so now the spring, when you turn off the acceleration, the spring is not at equilibrium at x prime. Okay, the spring will seem like it's overstretched at x prime. Okay, let me walk this through one more time. When we are accelerating, we are stretching the spring beyond the normal equilibrium to x prime, and we are establishing a new equilibrium prime. This is when the spring mass system is at an equilibrium while we are accelerating upwards. Okay, but when you turn off this acceleration and the acceleration goes away, this equilibrium prime is now not an equilibrium for the system, in that x prime is a location that is beyond the regular equilibrium, and therefore the object will start to go back to the original equilibrium. This is equilibrium original. This is equilibrium prime. Let me use a different color, blue. Okay, and so we will actually see the object M will move upwards, and that is when we want to stop the clock. Stop when mass starts to move upwards, not when it hits the middle. Okay, so we start the clock when the elevator starts, and then stop the clock as soon as the mass looks like it's moving upwards. All right, that's all we have time for. Tomorrow we'll go over the other one and then look at the College Board platform to do your AP test. If you're taking an AP test, good luck. Make sure you watch those videos. You can always watch the AVC stream from last Friday if you want to look at how we use the platform, but I'll go over that tomorrow for AP1. Right, you still have some MyAP MCQs to finish up this week, so make sure you do those stuff. Continue to work on it. You have your final on the 22nd. What does this time give us? Velocity. Use my key. V equals V0 plus AT. We're starting from 0, so V is equal to A times T. All right. Thanks for tuning in. I'll see you next time.